Welcome to today's webinar with the title ZIF Contacts, Selection and Design of the Interface at RIGID.flex. I am Andreas Schirp, your host of today's Würth Elektronik Circuit Board Technology webinar, and I would like to welcome you. The speaker of today's webinar is our expert in RIGID.flex, Werner Oechslen, from our Technical Project Management at Würth Elektronik Circuit Board Technology. Welcome, Werner. And now, I wish you lots of fun and new information.
Thank you, Andreas, and also hello and welcome from my side to today's webinar here. The content we speak about today is ZIF contacts, so selection and design of the interface at RIGID.flex. So this is all mainly out of the view of the PCB supplier, yeah, which things should be considered. But before we start, let me briefly introduce myself. So my name is Werner Oechslen. I work now for Würth Elektronik since more than 15 years in the field of flex and flex rigid PCBs. Yeah, I'm now in the technical project management, where we look for, I would say, a little bit more than the standards, or a little bit special things, which customers come to us, and we try to support our production there for producing this and getting a new standard there. Yeah. You can see here the agenda of today. First, a little bit about the ZIF interface. So what applications, what advantages, what is a ZIF interface we speak about. Then the next step is the ZIF connector type. It's the type you're searching for, yeah, where the ZIF contact at the end is plugged in. The third point is the ZIF contact itself, so mainly on a FFC, FPC. We speak there about similarities, differences, processes like laser cutting, then an overview about the stack-ups and the first surface of such contacts. The last point, again, back to the interface, a little bit about the applications, where can I use a ZIF, where not, some tips and tricks, and at the end, a summary. Good. At the beginning, I would like to say, so ZIF contact, RIGID.flex. So I would say today, nearly each fifth design of a flex rigid PCB has such a ZIF contact, and we, as the, I would say, as the producer of the contact itself, have sometimes, I would say, a problem with the specification, the connector, and so on. And in the webinar, I try to explain to you which are the main points you must consider by, I would say, by searching such a connector type. Yeah. So we are starting now with the interface itself. So ZIF, the word itself, Zero Insertion Force. So what are the applications, advantages? The main thing, it's a detachable and cost-effective connection, which could be, I would say, plugged in several times. So we say roughly max 30 times. If I hear it from some connector suppliers, we can have modular system structures. That means maybe you have a main PCB, something, or a main function of a PCB for high volume production, and you have maybe another subsystem, a modular system with another PCB, which is customer special designed, and you could plug in this, or you could have this then together in an interface. Also, another advantage is this low construction heights, and also the low weight of such a connector, and also, yeah, the complete interface. So we have on the one side the connector, on the other side we have a cable, so a ribbon cable maybe. It's then called FFC, flexible flat cable, or we have customized rigid flex PCB, which is then called at the end FPC, also flexible printed circuits. So as you know from PCB production, so we have for FPC a lot of more tolerances to consider as for FFC construction. So for FPC, we have to consider plating, copper thicknesses, and so on, the pressing itself. So, but more detailed, I will explain this later. To end up this, I will say this overview, so that we speak the whole webinar from the same things. So ZIF interface at the end is on the one side the ZIF connector, which you design on your PCB, and the ZIF contact, which we as the PCB supplier have to manufacture at the end. But at the end, if you're searching for a ZIF connector, it is defined which ZIF contact must be used through from tolerances, thicknesses, and so on. On the right side, you can see a typical application of such an ZIF contact. You could see here the connector itself with this red color roughly, and you could see here the RIGID.flex PCB. It's here a 2-layer rigid part, and the flex layer is only with 1 copper layer. Yeah, you could see there the gold contacts which are inserted or plugged into this connector. So this is a typical application. It's here an system for inventory management with a laser scanner. Yeah, so it's an adapter for an upgrade from the display, which you could see here at the end, the whole housing of the system. Okay, now we know what it is. Now we come first to the connector types. Yeah, as you know, there are a lot of different connector types to cover, I would say, each customer needs. Yeah, maybe you could see here with the 1 second. See here, so pointer. Now you could see here with a special locking. It's also here with a locking. Here is it with a locking. That means this FPC or FFC is locked inside the connector from against pulling out. ZIF types, for example, it means the mechanisms for closing it. It's back lock, front lock, or flip lock, and also non-ZIF or LIF contact. So LIF means low insertion, ZIF zero insertion. That means there's no additional locking for it. You will only put it inside a connector, and it's closed by the spring contacts from the connector itself. Yeah, and we have a lot of options here. It's the number of the contacts, the pictures of the contacts, the surface. There are special high-speed connections, the locking, contacting above or below. Then it's also the area of application is very important. Standing, lying, and 1, 2 rows of contacts depending on the pitch of the PCB. So we have here different options. So what we as the PCB supplier, we make very often the experience that only these criteria are decisive for the selection of the connector type. Yeah, so we as the PCB supplier see this a little bit different. Yeah, so the counterpart, so that means the part which is connected or which is plugged in this connector type is much more important for us. So we are looking now for the ZIF contacts itself. So you could see them here. So these are normally defined by the connector type, here with some mechanical locking and so on. So what are the similarities? Yeah. So similarities of all contacts are that we have small contour tolerances, like you can see here, red marked. What we also have, small tolerances from the contacts to the contour of the ZIF contact. That means the registration from the pads to the contour. And the last point, small radius at the interlocks. Yeah, here a little bit more detailed. So you can see here the interlocks. There's a radii here, for example, of 0.2 millimeters. And the other contour tolerances are mostly plus minus 50 or plus minus 70 micron. Yeah. So what are now the consequences for us as the PCB supplier? So the consequences are that we have such small tolerances and radius that it's no more possible by a milling process. So what we are doing, we are cutting generally the contours of such ZIF contacts by laser. Let's look now a little bit more detailed for the laser cutting. So you can see here some pictures of the laser itself. So what are the advantages? So a real big advantage of the laser is the registration of the laser via the conductive pattern. So the tolerances from the contacts to the contour are not a problem. Yeah? One more thing is the advantage is the connection of the I would say the connection to the delivery panel. Yeah, that we do this laser cutting process, and you as the if you have assembled a PCB and want to have it out of the delivery panel, it's much more easier. You could see here the picture. You could see here the laser contour. So the laser contour has at the end a width of only 50 micron. And you could see here such small laser micro bridges. Yeah, these bridges have only, or tabs have only a width of 150 to 200 micron, and they are really easy or simply to break out here. So it must not be milled or something else. One more advantage is the delivery panel at the end. It is much more stable. You could also see it here in the picture. That means that the FR4 material you could see here remains unglued under this flexible area. And the last advantage is by this laser cutting that we could have an optimized delivery panel to have at the end smaller distances in between the PCBs, and we are getting more and more PCBs on our production delivery panel at the end the production panel. So the costs of the PCB is going down here because we don't need, I would say, this milling diameter of 2 millimeters in between the several flex and rigid parts. So these are now the general points regarding the laser cutting. We are now looking for the differences of such ZIF contacts. Yeah? The main difference, what we have the experience as the PCB supplier, is the thickness tolerance of the PCB. So standard tolerance, you could see here on the right side, is so the standard thickness at ZIF contacts is this 0.3 millimeter, and the standard thickness tolerance is plus minus 50 micron. We also have advanced requirements, as you can see here, with only a tolerance of plus minus 30 micron. And we also have a lot of specifications for such ZIF connectors, which have a smaller tolerance than this plus minus 30 micron. So like in this case, it's 0.29 to 0.34 millimeters. This is no more possible for the PCB production. Yeah, these tolerances are at the end too small. What are our consequences now for the production? So if we get such a data sheet, so standard for us is plus minus 50 micron. We could use an FR4 stiffener, which is produced via an automated depth milling process. And we also have this advanced solution. It's with a polyamide stiffener, which is glued on the flex part. And there we have a thickness tolerance of plus minus 30 micron. Yeah, so at the end, it's very important to search at the beginning for the right connector to don't have at the end any problem that no PCB supplier maybe could produce this contact with the mentioned tolerances. So now let's look a little bit more detailed into FR4 stiffener, polyamide stiffener. What is this? On the left side, you could see now this FR4 stiffener. I will show it here. You could see here, it's from the back side. We are doing here a controlled depth milling and could have with this depth milling a thickness tolerance of ±50 micron. It's an automated depth milling process and it's no extra process because for flex rigid PCBs, we need at every flex rigid intersection such a depth milling process. You could see here, that's the intersection from the rigid at the end to the flex part. So it's no extra process, it takes a little bit longer at the depth milling process. You could also see here this laser contour cut by laser, and also here the FR4 material which is remaining under this flex area. So this is the one thing. So if you have chosen the right connector, is it possible? If you have a more advanced connector at the end, we need to use a polyamide stiffener with the tolerances at the end, thickness tolerance of ±30 micron. So what is this, the end or the result for our production? We have more effort and we have at the end higher costs for the production of such a stiffener. As you can see here, the polyamide stiffener, so it must be cutted in this case as a single part, and at the multi-layer process we have this as a puzzle inlay inside the multi-layer and is then, I would say, at the end pressed to the contacts from the backside here. So it's a manual process, and depending now on the, I would say, on the size of the ZIF area, on the delivery panel, how is this done, if we could do stripes and so on. So depending on this, it's for sure more effort and higher costs. Why polyamide stiffener? So it could be if you have maybe a small pitch smaller than 0.5 millimeter for such stiff contact, it could be that it's not more available. I would say thickness tolerance of ±50 micron. Yeah. So, but for pitches more or equal than to 0.5 millimeter, so you could always find a ZIF contact with the wider thickness tolerances. So both variations are possible, but not for each stack up for a flex rigid PCB. On the left side, you could see now the F4 stiffener, the polyamide stiffener, and on the other axis, you could see our stacks. On the one side, 1F XRI means one flexible layer outside from the PCB and X rigid layers above. Or a 2F XRI means two flexible layers outside, so the top layer and the first inner layer. And the third main technology which we are producing is the XRI, 2F XRI stack. That means the flex is in the middle of the PCB. So here, stack for 1F XRI, both stiffener variants are possible. So on one side, you could see here depth milled, rigid part depth milled to the thickness, or here the polyamide stiffener glued inside. Same as for the 2F XRI stack, also possible depth milling and also the polyamide stiffener. For the two-layer flex inside is the depth milling process no more possible, because due to the flex in the middle, we have much more tolerances and we cannot hold, I would say, the ±50 micron from the thickness tolerance like for the other stacks. So therefore, we need to use a polyamide stiffener if the flex is inside. But this PCB is at the end much more expensive. That means we need here now nickel gold or gold process on the inner layer, and often the flex is bladed through, so then we need an additional blading process for the flex layer. So we have here alternative stacks which you could use. Cheaper alternative stacks at the end. So the one option is that we have at the end, you could see here the section, the cross section, the flex is coming, then we are doing a rigid part in front of the ZIF and have at the end the ZIF contact on the outer layer. So we could then have the depth routing process. So also you could see it here, yeah. We go by vias to the outer layer and then have the contacts on the outer layer. This is the one option to make all the stacks cheaper. The other option is done with a 2F XRI stack. That means the flex layers top layer and the first inner layer, and the production is in this case much simpler or easier compared to the flex inner layer. So we could have standard nickel gold process. We could do again the depth routing process for the ZIF contact, and we can contact the reference layer. So mostly the second layer is the reference layer. We could contact this layer by micro vias. Yeah, you could see here ZIF connector, and you could have here micro vias in this area. So it's much easier and also much cheaper than with the flex inner layer solution. Yeah. Okay, this was now regarding the stack ups for which stack up we could use with which stiffener. Now we come to the surfaces. So our standard surface, or also our recommended surface for ZIF contacts, is immersion nickel gold. I think also in our production, if I see, I think 99% of all our ZIF connectors, which we are producing on our RIGID.flex PCBs, have the standard nickel gold surface. That means 0.05 up to 0.12 micrometer gold is there on the surface. We have only, I would say, one handful applications where a galvanic gold or a hard gold surface is used. That means, what is it? What means if you're using a galvanic gold or a hard gold process? That means we need connections out from the contacts to the panel area for the galvanic contact that we could have maybe 1 or 2 micron gold on the surface of the PCB. So it's an expensive process at the end, and the next thing is we have then to mill the front side of the PCB because we cannot laser through the contacts here at the end. Yeah. So, and it's danger of copper burst here, and here we could only cut the sides by laser. So at the end, it's more efforts and higher costs. So if you are now looking for a connector, please look also for the surface, because normally it's recommended by the connector to have maybe only a little gold surface or single gold surface. Yeah. So yeah, you have to consider which is the right surface for you. But this is also, I would say, depending on the applications. Yeah. So we are now looking for the application conditions. So at the end, we say ZIF connectors, ZIF interfaces are cheap, but not a real reliable connections. For example, no dynamic forces may act on the interface. That means no dynamic bending of the flex, that we are getting a movement on the ZIF contact. No high vibration load we recommend that is used for such a ZIF interface. So what could occur? So we have here pictures now. You could see on the right side now is the gold layer can be rubbed off of the spring contacts because there's so much vibration on it that at the end you don't have any more gold surface on it. Yeah. This is mostly with a non-ZIF or LIF. That means there's no additional locking here. So that means the vibration goes directly to the contacts and we get maybe the gold off. Or what also happened at a customer example means that the contacts are broken at the intersection, I would say, from the housing or where the contacts get out of the housing. Yeah, that we have here too much vibration, too much forces, that we could have broken this brittle nickel and gold surface. So what we are recommending here, so we are recommending other plug connections for, I would say, such high reliable connections under vibration, dynamical bending. So we say the ZIF interface is not the right connection here. Good, we are now coming already to the tips and tricks. So some things which we have in our daily work, I will say, which customers are doing to make things easier, I would say, and to make it better producible at the end for our production. So one thing for customer handling means we're here with the ears. So I could have here a little bit. Here you could see these ears. These ears are still in the stiffener area, and on these ears you could have an easier handling. That means if you have a housing, you cannot go directly there, and you need a little bit more force to put in this connector. I would say in this contact in the connector. So as an option, another thing is if you have a 2-row version ZIF, so which you can see here, the 2 rows. The 1 row is the front, and the other row of the ZIF contacts is here. This is mainly, in this case, only a pitch of 0.3 millimeters, so the contacts can be directly next to the other. So we have a lot of specification where it's described at the end that the isolation distances, mainly in between, I would say, here at the ends, at the edges, is less than 100 micron. So for the PCB production, we need, if you have maybe an additional plating on the outer layer and so on, we need 100 micro isolation. So search for the right connector, or maybe the layout could be modified. So speak to us, we could speak about this. And on the right side, we could see now some tips and tricks for the polyimide stiffener. So you could see here in the middle, these are the stiffeners now, which are cut. So normally around 200 microns thick. You could see here the production panel. Here's the area with the milled prepreg and the milled core, where this, I would say, this polyimide stiffener is done like an inlay. I would say it's a puzzle here. Now it depends on how many PCBs, ZIF contacts you have per panel. So the handling at the end, the manual handling is going up and up. So we recommend put your ZIF contacts in a row, like here, one ZIF contact, next ZIF contact. So you could connect the stiffener, and we reduce at the end the manual effort here. So we give you the option, come to us. We could give us your PCB size, your PCB data, and we could define together such an delivery panel to get also the optimal workload at the end. Good. So we come already to the last page from my webinar. So summary, which we have heard here. So as I said, the ZIF interfaces are not suitable for all application conditions, vibration and dynamical bending. So maybe another solution is here better to get a reliable interface. The next point is the laser cutting. This is on the one side necessary to reach the tolerances and the connector and the locking systems for the radis. And also you could have advantages with the delivery panel. On the one side, we are getting more PCBs on it, and on the other side, you have an easier breaking out in your house. Third point is the selection of such a suitable ZIF connector, and at the end, also the PCB stack card save efforts, and at the end also the costs. So it's very important that you're searching for the right ZIF connector, that at the end this PCB manufacturer could use, I would say, a standard stack and also a standard method for producing such a contact. And the last point, so if you have maybe you are searching for a connector, send us the data sheet, send us the PCB, send us the contour of the PCB, so we could support, is it the right connector, or it is better to use another connector. And we could also give you, we could also suggest you a better delivery panel to get the perfect thing in costs and production. So we are now already at the end. I will say thanks for your attention, and I will hand over to Andreas.